In-memory computation and parallel processing are the two major reasons why Apache Spark is used in the industry and is one of the best frameworks to handle big data and perform analysis. Now, there's an important term known as RDD, which serves as the backbone of Apache Spark. So, guys, today I, Kisle from Edureka, will guide you through this session on PySpark RDD. So, before moving forward, let's have a quick look at today's agenda. I'll start off this video by giving you a brief introduction on why exactly we need RDD. Next, I'll explain you in detail what are RDDs and what are the various features of PySpark RDD, along with the various operations that can be performed on it. Next, I'll show you guys some demo related to transformations and actions that can be performed on these PySpark RDD. And finally, I'll finish off this video by giving you a demo on page ranking algorithm via PySpark RDD. When it comes to iterative distributed computing, that is, processing data over multiple jobs in computation, we need to reuse or reshare the data among multiple jobs. Now, in earlier frameworks like Hadoop, there were many problems while dealing with multiple operation jobs. We need to store the data in some intermediate stable distributed storage such as SDFS. Now, the multiple input-output operations make the overall computations job slower, and there were replications and serializations, which in turn made the process even more slower. Now, our goal here was to reduce the number of input-output operations through the SDFS. This can be only achieved through in-memory sharing data. The in-memory data sharing is 10 to 100 times faster than network or disk sharing. Now, RDDs try to solve all these problems by enabling fault-tolerant distributed in-memory computations. So let's understand what are RDDs. Now, RDD stands for Resilient Distributed Data Sets. They are considered as the backbone of Apache Spark. As I mentioned earlier, it is one of the first fundamental data structures. Now, these are schemaless structures that can handle both structured and unstructured data. The data in RDD is split into chunks based on a key and then dispersed across all the executor nodes. RDDs are highly resilient, that is, they are able to recover quickly from any issues as the same data chunks are replicated across multiple executor nodes. Thus, even if executor fails, another will still process the data. Now, this allows you to perform your functional calculation against your dataset very quickly by harnessing the power of multiple nodes. Now, RDD supports two types of operations, namely transformations and actions. So basically, transformations are the operations which are applied on an RDD to create a new RDD. Now, these transformations work on the principle of lazy evaluation. So what does lazy evaluation mean? What it means is that when we call some operation in RDD, it does not execute immediately. Spark maintains the record of which operation is being called through a didactic acyclic graph known as DAG. And since the transformations are lazy in nature, so we can execute operations at any time by calling an action on the data. Hence, in lazy evaluation, data is not loaded until it is necessary. Now, this helps in optimizing the required calculation and recovery of lost data partition. Now, actions on the other hand are the operations which are applied on an RDD to instruct Apache Spark to apply computation and pass the result back to the driver. Now, the moment an action is invoked, all the computations happen which are in the pipeline. This gives us the result and which is stored in the intermediate storage or a distributed file system. Now let's have a look at few of the important transformations and actions. We have certain transformations like map, flat map, filter, distinct, reduce by keep, map partition. Do not worry, I'll show you guys exactly how these work and what are the use of all these transformations. And under actions, we have collect, collect as map, reduce, count by key, we have take, we have count by value, and many more. So let's have a look at some of the important features of PySpark RDD. First of all, is the in-memory computation. RDDs have a provision of in-memory computation, which makes the process even more faster. Now, all the transformations are lazy. As I mentioned earlier, it does not compute the result right away. RDD track lineage information to rebuild lost data automatically. Therefore, it is fault tolerant. Now, data can be created or retrieved anytime, and once defined, its value cannot be changed. This refers to the immutability of data. Partitioning is the fundamental unit of parallelism in PySpark RDD, and users can reuse RDD and choose a storage strategy from them, which implies for persistence. Now finally, it applies to all the elements in the dataset through maps or filter or group by operation, which implies that it successfully handles coarse grain operations. Now there are three ways to create RDDs. One can create an RDD from parallelized collection, it can be created from another RDD, or it can be created from external data sources like SDFS, Amazon S3, HBase, or any database of that sort. So let's create some RDD and work on them. So I'm going to execute all my practicals in the Jupyter notebook, but you can execute it on the shell as well. So to create an RDD from parallelized collection, we use the sc.parallelize method. Now sc stands for Spark context, which can be found under Spark session. The Spark session contains Spark context, the streaming context, and the SQL context. It has been changed after the release of Spark 2.0. Earlier, Spark context and SQL context, as well as the streaming context, all were distributed separately and had to be loaded separately. Now the sc.parallelize method is the Spark's context parallelize method to create a parallelized collection. This allows Spark to distribute the data across multiple nodes instead of depending on a single node to process the data. So as you can see here, I am creating a list. So I have assigned Ross as 19, Joey 18, Rachel 16, Phoebe 17, and Monica 20. Now that we have created our RDD, which is my RDD, we will use the take method to return the values to the console, which is our notebook, and we will also execute an RDD action, which is the take. So guys, if you remember, as I told you earlier, when an action is invoked, all the computations which are lined in the graph or the lineage graph of the transformations which have been performed on the RDD take place all at once. So a common approach in PySpark is to use the collect action, which returns all the values in your RDD from the Spark work nodes to the driver. Now there are performance implications when working with a large amount of data, as this translates to large volumes of data being transferred from the Spark worker nodes to the driver. For small amounts of data, this is perfectly fine, but as a matter of habit, you should pretty much always use the take method. It returns the first n elements which are being passed to as an argument to the take action instead of the whole data set. It is more efficient because it first scans one partition and uses those statistics to determine the number of partitions required to return the result. So as I have 6 elements in my RDD, I'm going to use my RDD.take, and as an argument I'm going to pass 6. So guys, as you can see here, this is the output of the RDD. Now another way to take an input of a text file is through sc.textFile method, and here you need to provide the absolute path of the file which you're going to use. So I'm creating a new RDD here, and to have a look at the new RDD we are going to use take method to have a look at the first 5 elements. So as you can see, we have the first 5 elements, the first one, the second one, third, fourth, and fifth. Now we can also take any CSV file as an input through sc.textFile. So I'll show you guys how it's done. So guys, here we are going to use the sc.text file with the absolute path. As you can see, I'm loading a FIFA players.csv. Now there's another argument I've passed here, which is minimum partitions. Now it indicates the minimum number of partitions that make up the RDD. The Spark engine can often determine the best number of partitions based on the file size. But you may want to change the number of partitions for performance reasons, and hence the ability to specify the minimum number of partitions here. And after that, we have used the map transformation. Now here we use the map function to transform the data from a list of string to a list of lists. We are going to use the lambda function. Now putting the sc.text file and the map function together allows us to read the text file and split it by the tab delimiter to produce an RDD composed of a parallelized list of list collections. So if we have a look at the first 3 elements of this particular RDD, as you can see, we have 201, which is round ID, match ID, team, the initials. Now to have a look at the number of partitions which we applied, in general, it takes up the partitions automatically, but in case if we want to get the number of partitions for a particular RDD, we use the getNumPartitions method. So here we have specified it 4, so the output should be 4, I guess. Yes, the output is 4. And now if you want to have a look at the number of rows in a particular RDD or the number of records in a particular RDD, we use the count method here. So guys, as you can see here, we have 37,000 number of rows. So this was our RDD, the sample text file which we took. Now suppose I want to convert all these data into a lowercase and I want to divide all these paragraph into words. So for that we create a user defined function. So I'll show you how it's done. So guys, as you can see here, we have created a function which will use the dot lower and dot split transformation. So we are creating a new RDD here, which is the split RDD, and we'll pass the new RDD through this function using the map transformation. Now map is basically used for executing a transformation on each and every element of that particular RDD. So if we have a look at the output of the split RDD, so guys, here you can see all the elements are separated now by individual words and all of them are in lowercase, right? Now next what we are going to do is we use the flat map transformation. Now it is similar to map, but the new RDD flattened out all the elements. So let us use the flat map transformation. And if we have a look at the RDD, as you can see, the output is flattened. It's not vertical, it's horizontal in nature, which is more easily readable. Now here I'm going to create a stop word RDD, which contains a few of the stop words, common stop words. I'm not using all the stop words here. So what my agenda is here is I want to remove all the stop words from this particular RDD, which we have here. So for that, we are going to use the filter transformation. We are providing a lambda function here. We have defined lambda function x such that x not in stop words. And we are creating a new RDD, which is RDD1, and we are going to filter out the results from the above created RDD. So if we have a look at the output of this new RDD, which we are going to create, most probably it won't be having the words which are defined in the stop words RDD. So as you can see, output 13 contains contracts, transactions, and the, whereas output 15 contains contracts, transactions, and the are mentioned in the stop words list, so they are not included in the new RDD. For that, we use the filter transformation. Now, filter can be used in many ways. Mostly it is being used with the help of lambda functions in PySpark RDD. So what I'm doing here is I'm creating a filter RDD which will contain all the elements which are starting from C. Here I'm using the lambda function x such that x starts with C. So let's have a look at the output of this new filter RDD. Another important thing to notice here that I'm using the distinct transformation, which returns a new RDD containing the distinct elements on the source RDD. So as you can see here, we have control, claim, code, computing, connections, case, car, all the elements starting from C. Now next what I'm going to do is execute a small program of word count. I hope you understand what word count is. The output of this will basically give us count of each particular word. Here I'm taking the output of the first 10 words. So for that I'm using the map function lambda x such that x will be provided with the value 1. Now I'm grouping it by key. I'm using the group by key method here. It is used to group the data according to the particular condition. Now I'm creating another RDD which is RDD frequency, which will take the input of RDD group and it will map the values with the sum. It will create the sum of the particular key, which will be the word, and then I'm again using another transformation of map, and then sort by key is given as false. So the output will be in the same format as the input, but we'll get the word count as well. So let's have a look at the top 10 words and see what are the count. So as you can see, and has 48 counts, D has 38, and so on. We can see that they has 7. So the initial RDD1 which we created after removing all the stop words contains 660 rows. So now I'm going to use the distinct method here to see what are the distinct elements which will be in RDD2. So if we do RDD2.count, it most probably should be less than the RDD1 count or equal to it. So guys, it's 440. So 220 stop words were removed from the list. Now suppose I want to have a look at the elements of this RDD2 which I created, and I want to see the elements which have the first 3 letters same, as in similar first 3 letters. I'll show you the output, you'll understand. As you can see, we have EDG and EDGS, which is edges. We have yeah and years, ALG, algorithm, ROB, robust, SCA, scale. So if we execute it for 2, we see we have GU guide, GR, groundwork. We have growing, gradual, grind log, graphics, gradually. We have such, transmission, gains, gained, gain. These are small tricks which will help you to execute your code faster with the help of RDD. Now next I'm going to use the sample method. I'm creating a new RDD which is sample RDD, and I'm passing the RDD1. And as you can see here, I have two arguments which are false and 0.1. Now what does this mean? Now false is basically is the width replacement parameter. So suppose I want the output to not have all the replacements. So I'm going to assign false. And 0.1 is basically the fraction of data with which we are going to take the output. We are going to take the sample, I rather say. So here I'm going to take 10% of the original data, rdd1.sample. So rdd1 contains 660 rows. So 10% of that must be around 66 or 67, I'd say. So let's collect our sampled RDD. So if we take the count of the new sample RDD, as you can see, it's 51. It's very much around 66. And as we have used false here, so it's showing us without replacement. So if we have a look at the output of, say, the sample RDD, it will contain a sample from the original RDD. You see we have contrast, establish, race. Now next what we are going to learn are some of the functions like join. We have reduce by key, sort by key. We are going to look at unions. So for that I'm creating two RDDs which are the key value pairs. So A has A given as 2 and B as 3. And similarly we have B containing A value 9, B value 7 and C value 10. So in order to join this RDD, I'm going to create another RDD which is C. And the method to join these two are like, I'm going to join A with B. So I'll use A.join, and in join I'll give the parameter as B. So if we have a look at the output of C, now here I'm using collect because C has very small amount of data in it, but it's advised to use take as well. So looking at the value of C, we can see that A has two values, 2 and 9, and B has two values, 3 and 7. Now this is one kind of join. Similarly, you can perform any types of join like left join, left outer join, right outer join. Now here I'm going to create a num RDD which will take all the numbers from 1 to 50,000. Now here I'm using the method range to get all the numbers in between 1 to 50,000. Next, we are going to use the reduce, another action which reduces the elements of an RDD using a specified method. So here the method is a lambda function x and y such that the output is x plus y. So this will give us the sum of numbers from 1 to 50,000. So as you can see, the sum of numbers is pretty huge. So next I'm going to use the reduce by key method here. I'll show you the importance of that function, or I'll say the action. It works in the similar way to the reduce, but performs a reduce on a key-to-key basis. So as you can see, the data key data has certain numbers assigned to the alphabets. We have A4, B3, C2, A8, D2, B1, D3, and we have given another parameter which is 4. Now this is the number of parallel tasks to be executed while taking the input into the data underscore key data RDD. And as you can see here, we have reduced by key. We are using the same lambda function. So as you can see in A, we have 12, which is the sum of 4 and 8. In D, we have 5. D has 2 and 3. C has 2 and B has 4. B has 1 here and 3 here. So in order to save your file, you use the save as text file method here. So we are going to save the values of RDD3 into a file called data.txt. Here you need to provide the absolute path where you want to store the data. So let's check out where our data is stored. So it's under desktop. So as you can see here, we have one folder created which is data.txt, and inside that we have the part files and the success file. So as you can see, it contains all the elements. So here I'm creating another RDD test to show you the sort by key function and how it works. The sort by key transformation orders the key value RDD by the key and returns an RDD in ascending or descending order. So by default it's ascending, but you can also use it to get the output in the descending order. So as you can see, I'm using the sc.parallelize and I'm taking the test, and I'm using the sort by key, true and 1. Now true is for ascending. So as you can see, I have 1, 3, 2, 5, A1, B2 and D4. 1 comes first, then 2, then A, B and D. That is in the ascending order of the key. So next we are going to learn about union, how union works. Now the union transformation returns a new RDD, which is the union of the source and the argument RDD, which is being passed. So here we have two RDDs, which are union underscore RDD and union 2, contain certain elements. So if you want to take the union of these two RDD into a new RDD, or just want to see the output of this union, we are going to use the union method here. You can see the syntax is pretty simple here. So as you can see, it created the union of these two RDDs. Similarly, intersection also works in the similar manner. Now next what we are going to learn is the map partitions with index. Now it is similar to map but returns the f function separately on each partition and provides an index to the partition. Now it is useful to determine the data skew within partitions. So for example, I have the function f here, which is split index and iterator, and yield split index. I've created mpwi, which is the map partition with index RDD. It's just a name. It's not necessary to name your RDD like this, just for the sake. And if we do the sum, you can see the sum output is 6. So as you can see, we have two RDDs here, A and B, and I'll show you how intersect works. It's in the same similar fashion as union. Now what it gives is the intersection of these two sets. So now what it will do, it will produce an RDD containing elements found in both RDD. So ideally it should give us the output of 3 and 4, which is common to both RDD. So let's see how it can be implemented. So guys, as you can see, the output is 4, 3. That is what we expected. Now we are going to use the subtract method. What it will do is subtract the set B, RDD B from RDD A. Okay, so the output should be 1 and 2, I guess, rather say 2 and 1. Now, another interesting thing to consider is the Cartesian product. We use the Cartesian method here to get the product of RDD A and B. So as you can see, every element of RDD A has been mapped with every element of RDD B. So guys, I hope you all understood a lot about the transformations and actions and the operations which can be performed on RDD to get your certain output. So guys, let's do something interesting now. So what we are going to do is, here we are going to find the page rank of certain web pages, and we are going to use RDD to solve this problem. So let's understand what is page rank first. So page rank is basically the rank of any page which is being developed by Google. So the page rank algorithm, as you can see here, contains a certain formula. So the algorithm was developed by Sergey Brin and Larry Page. Larry Page is the person after which this PageRank algorithm has been named. And these developers of the PageRank algorithm later founded Google, which is why Google uses this PageRank algorithm and is one of the best search engines in the world. Now, PageRank of a particular web page indicates its relative importance within a group of web pages. The higher the page rank, the higher up it will appear in the search result. Now, the importance of a page is defined by the importance of all the web pages that provide an outward link to the web page in consideration. So for example, let's say that a web page X has a very high relative importance, then web page X is outbounding to web page Y, hence web page Y will also have a very high importance. Do you get me? If we have a look at the formula here, which we have, so basically the page rank of a particular page at the particular time is equal to the summation of all the page ranks of the inbound link divided by the number of links on that page. Now to get a clear idea about this, how it works, let's take an example here. We have 4 pages. We have Netflix, Amazon, we have Wikipedia and Google. So initially what we do is assign the value of 1 to all the pages. Keep that in mind. So according to our formula, in the 0th iteration, what we do is to get the page rank, we divide it equally among all the number of pages which are there in the network. So the page rank at iteration 0 for Netflix is 1 by 4, for Amazon it's 1 by 4, for Wikipedia it's 1 by 4, and Google is 1 by 4. Now this is the initial iteration, so it doesn't count. So from iteration 1, if we have a look at the formula, so suppose we are talking about Netflix, right? So if you look at the formula, it says page rank of the inbound link divided by the number of links on the page. So Netflix has Wikipedia coming to inbound. The inbound link to Netflix is only coming from Wikipedia, right? So we need to consider Wikipedia now. So the previous page rank of Wikipedia is 1 by 4, and now we divide it by the number of outbound links going from Wikipedia, which is 1 going to Netflix, 1 to Amazon, and 1 to Google. So it's 1 by 4 divided by 3, which gives us 1 by 12. Okay, so let's have a look at the Amazon first. So Amazon has inbound link coming from Netflix and Wikipedia as well. So it will take the summation of Netflix and Wikipedia. So considering Netflix, we have 1 by 4 as the previous iteration divided by the number of outbound links from Netflix, which is 2. So 1 by 4 divided by 2, that's 1 by 8. And then we'll add it for Wikipedia as well. So for Wikipedia, it is 1 by 4 divided by the number of outbound links, which is 1, 2, and 3. So it's 1 by 8 plus 1 by 12, which is 2.5 by 12 if you do the calculation. So this is how the PageRank algorithm works. Now we'll implement the same using RDD. So let's go ahead and get started. Now, so for our example, we are having 4 pages which are A, B, C, and D. Now consider here D has 2 inbound links. Okay. So we'll do the summation, which is first coming from A and the second one which is coming from B. As stated earlier, it will be the summation of previous page rank of A divided by the number of outbound going links, which are 1, 2, and 3 for A, and for B it's 1 and 2. So let's see how it can be implemented. Now step 1 is creating nested list of web pages with outbound links and initializing ranks. Okay, so let's get started. So here I've created an RDD which is page links. So for A, the outbounds are B, C, and D. For C, it's B. For B, it's D and C. And for D, it's A and C. So first, initially, we'll assign the page ranks as 1, as I mentioned earlier. Now, after creating ranks for the nested list, we have to define the number of iterations for running the page rank. Now, we are going to write a function that will take 2 arguments. The first argument is on our function is the list of web pages, and which will provide the outward links to the other web pages, and the second argument is the rank of the web page accessed through the outbound links that are the first argument. Now the function will return contribution to all the web pages in the first argument. So as you can see, our first argument on our function list of the web page is the URIs, and the second one is the rank. Now the code is very explicable. Our function rank contribution will return the contribution to the page rank for the list of the URIs, and which is the first variable, and the function will first calculate the number of elements in our list URIs, and then it will calculate the rank contribution to the given URIs, and finally for each URI the contributed rank will be returned. So let's first create our pair RDD of the link data, and then we are going to create the pair RDD for our rank data as well. As you can see, the rank is 1. Now, next what we are going to do is create the number of iterations, which is 20, and we'll have S defined as 0.85. Now, S is known as dampening factor. So let's assign these values. And now it's time for to write our final loop to update the page rank of every page. So as we have defined the number of iterations as 20 and with the dampening factor as 0.85, so let's compute it. So now if you have a look at the output of the page ranks, so guys, as you can see in the 49th block, there is no actions performed. Okay, so the actions which you are going to perform is in the 50th block, I'd rather say. So what it'll do, it will run this loop through 20 iterations, and to confirm that, you can go to the console and you can see here the processes are running. So this will take a certain amount of time based on the number of iterations which we have, and this will give us the final output of the ranks, I'd rather say. Now, so let's investigate our loop first. So first we join the page links RDD to the page ranks RDD via an inner join, And then the second line of the for block calculates the contribution to the page rank by using the rank contribution, using the rank contribution function we defined previously. And the next line, we aggregate all the contributions which we have. And in the last line, we update the rank of each web page by using the map function. So as you can see, we have the output of B as 0.22, D 0.24, and A 0.25. Now the dampening factor also plays an important role here. Now the value of C must have been even lesser than the value of A, B, and D. So we can say that A has the highest page rank, followed by D and then B, and the minimum has to be C. Now one thing important to note is that the sum of all the page ranks is always equal to 1. So suppose if we look back at our problem there, as you can see in the iteration 0, if we add all the elements here, 1 by 4 plus 1 by 4 plus 1 by 4 plus 1 by 4, that is 1. In the iteration 1, if we add 1 by 12 plus 2.5 by 12 plus 4.5 by 12 plus 4 by 12, that will give us 1 again. And similarly, it's for the iteration 2. So more the number of iteration, more will be clearer output, and we can get more accurate output here. So this is it, guys. I hope you learned about RDDs, how they implement the in-memory computation, the lazy evaluation, how transformations and actions are used in RDDs. And I hope you got to know more about the PageRank algorithm and how to implement certain algorithms using RDD and make our life easier. Thank you for watching.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!